Hello everybody, this is Bert Dixon here presenting on the topic of sequences to go along with section 10.1 in your Thomas Calculus book. Before starting this video, you'll want to print the note template that goes along with this. You can get to that by going to bit.ly/DixonMath, and that is case sensitive. So you want to make sure the D and the M are capitalized. So bit.ly/DixonMath, and that will take you to my course website, and click Math 2. And then find the note template for 10.1, which is here. So go ahead and download that, print it, and come back and watch the rest of the video. So this lesson is on sequences, and there's really not much calculus involved in this section at all. This is really an introductory section. We are going to be working with sequences and series quite a bit in chapter 10, and so this section is really to just help you become acquainted with sequences and the notation and terminology that goes along with them. So you're not going to see any derivatives or integrals or anything like that unless we use it. Maybe we'll use a derivative to apply L'Hopital's rule in a couple of problems. But other than that, you're not going to see a lot of calculus. So what is a sequence? A sequence is just a list of numbers. So for example, you could start with the number 5, and then the next number we list as 7, and the next number we list as 9, and the next number we list as 11, and we could go on and do this forever. Another possible sequence, maybe we'll start with the number 200, and then the next number is 100, and then the next number is 50 and 25, and so on and so on. Another example of a sequence could be just the same number listed over and over: 4, 4, 4, 4, and so on. It's not a very interesting sequence, but it is an example of a sequence. Another possible sequence might be 2, -2, +2, -2, and so on, going on forever in that pattern. So what we're going to look at in all of the sequences that we study is we're going to try to determine whether the sequence converges or diverges. So that means, does the sequence approach a particular number? So the definition says that a sequence converges if this limit exists, meaning the terms are approaching a certain number L, and L must be any real number. L cannot be infinity or negative infinity. It has to be a real number. And so if the limit exists, meaning that it approaches some real number L, then we say the sequence converges. And if the limit doesn't exist, meaning it's infinite, it's maybe approaching infinity or negative infinity, or if the sequence just isn't approaching any number at all. So for example, this sequence, it's not getting really big, it's not getting really small, it's not approaching any particular number, it just keeps going back and forth between -2 and +2. We would say that this sequence diverges as well, because it is not approaching a particular number. Here's an example of a sequence that diverges because its terms are getting larger and larger and larger without bound. It's approaching infinity. The terms are approaching infinity. So if it's growing without bound, then we say it diverges. And so we'll see in some examples coming up of what a convergent sequence looks like, and that is when we can evaluate this limit and show that it equals some real number L. So let's go ahead and take a look at our first example. This is our what we call our term generating formula, A sub n. So this tells us how to calculate each term. So we can make a list of the numbers in our sequence by starting with A sub 1, so that means the first term, and since 1 is the subscript, we're going to plug in 1 for all of the n's. So this number and these numbers need to match. So when n is 1, we get 1 plus 1 over 1 plus 3. So that is 2 over 4, or 1/2. when a is 2. So a sub 2, when n is 2, we get 2 plus 1 over 2 plus 3, and so that is 3/5. And so we can start listing this out now. Our sequence starts with 1/2. Our second term is 3/5. If you plug in 3, you're going to get 4 on the top and 6 on the bottom, which reduces to 2/3. When you plug in 4, you're going to get 5 on the top and 7 on the bottom. And so this pattern continues forever. And so we want to decide, is this approaching a particular number, or is it growing infinitely large? Is it not approaching any particular number? So the easiest way to determine that is by using the limit. So we're going to look at the limit as n approaches infinity of n plus 1 over n plus 3. So there's a few ways to evaluate this limit, just to review some things from Calculus 1 and actually a concept from Calc 2 as well. As n is approaching infinity, we might want to think about what's happening as n gets really large. So if we wanted to know what is the 1,000th term, that would be 1001 over 1003. And so you might recognize that this fraction is very, very close to 1. In fact, you can type that into your calculator and see that it is very close to 1. I could say 1001 divided by 1003 and see that that is 0.998, very, very close to 1. And so that might be enough evidence for you to realize that the fractions in this sequence are getting very close to 1. If I plugged in 10,000 for n, I'd have 10,001 over 10,003, which is even closer to 1. That is 0.9998. So we see we are getting very close to 1. We don't have to rely on the calculator to evaluate this limit. Some other methods that you learned in Calculus 1, for example, would have been to divide the numerator and denominator by the highest power of n that we see, which is n to the first power. So if I divide everything by n to the first power, then we see that that is the same as the limit as n approaches infinity of 1 plus 1 over n over 1 plus 3 over n. And this term is approaching 0 because as n gets large, that fraction gets very, very small. The denominator is getting large, and so the fraction is approaching 0. This is approaching 0 as well. So we see we just get 1 over 1, which is 1. So this limit is equal to 1. Another way we can see that this limit is equal to 1 is by applying L'Hopital's rule. Remember, when we learned L'Hopital's rule, we said if the numerator is approaching 0 or infinity, and the denominator is approaching the same thing, in this case infinity, then we can apply L'Hopital's rule, which says we can take the derivative of the numerator and denominator independently. So this would become the limit as n approaches infinity. The derivative of the top is 1. The derivative of the bottom is 1. And so there's another method that you could use to show that this limit is just equal to 1. Okay? So whether you're able to just see that this limit is equal to 1 by inspection, or you apply this algebraic method, or if you apply L'Hopital's rule, in all cases we get that the limit is equal to 1. So we say the sequence converges to 1. Okay, now let's go ahead and take a look at our second example, example B. Again, it's not required, but it's a good idea to list out a few terms so you can become acquainted with the sequence and have some idea of whether the terms are getting larger or smaller and whether they're approaching a specific number. So if I plug in 1, for example, a sub 1, put in 1 for n, we'd get 1 squared plus 2 over 1 plus 7. So that is 3/8. If I plug in 2 for n, a sub 2, our second term, is 2 squared plus 2 over 2 plus 7. So that is 4 plus 2 is 6 over 9, or 2/3. A sub 3 would be 3 squared plus 2 over 3 plus 7. So that is 11 over 10, and so on and so on. And so our sequence looks like this: 3/8, 2/3, 11/10, and so on. Just looking at those three terms, it's not real clear what's going on with this sequence. So we might want to try plugging in a larger number, like maybe 100. If we plugged in 100, we would have 10,000 plus 2 over 100 plus 7. And so that is 10,002 over 107. That is very close to 100. And then if you plugged in 1,000, so let's look at our 1,000th term. That's going to be 1,000,002 over 1,007. That number is very close to 10,000. And so we see by plugging in some larger numbers for n that this sequence just seems to be growing larger and larger and larger. Because after getting to the 100th term, we have 10,002 over 107, and then we go further to the 1,000th term, we get 1,000,002 over 1,007, and so these are just getting bigger and bigger and bigger, so it appears to be approaching infinity, but now we can also confirm that using the limit. The limit as n approaches infinity of n squared plus 2 over n plus 7. Again, there are a couple of ways you can evaluate this. We can evaluate this limit using L'Hopital's rule, because both the numerator and the denominator are approaching infinity. So we would get the limit as n approaches infinity of 2n over 1. And as n approaches infinity, the whole fraction is going to approach infinity. So we say the limit does not exist because it's infinite, okay? And so since this is infinity, that tells us this sequence diverges because the limit is not equal to a real number. So this sequence diverges. So we've seen one example now of a sequence that converges, and we showed that with the limit. We saw another sequence that diverges that we showed with the limit, because the limit in this case was infinite. In both of these examples, A and B, we were given a formula to find the nth term. So that is called an explicit formula. So this formula, for example, A, that's an explicit formula because we're able to explicitly find any term that we want. If I wanted to know the first term, second term, if I wanted to know the 100th term, I can do that. If I want to know the 10,000th term, I just plug in 10,000 and I can find that. So that's called an explicit formula. B is also an explicit formula because we were able to evaluate by plugging in any number for n, and we found the first term, the second term, the third term, the 100th term, the 1,000th term, and so these are both examples of explicit formulas. In example C, we're given a different type of formula. This is still A sub n still gives us a formula for generating the terms, but it's called a recursive formula, because in order to apply a recursive formula, you need to know what the starting point is and be able to apply the formula to get the next term. And so we always need to know some starting information in order to use what's called a recursive formula. So this is an example of a recursive formula. Actually, all of this information together gives us the recursive formula that we can use to generate this sequence. So let's see how this works. So for a recursive formula, we're given at least the first term. In this one, in this example, we're given the first two terms. So it says A1 is 1, A2 is 2. If I want to know A3, now I have to use the formula. So A3, by applying this formula, says we need A with a subscript 2 less than n, so this would be 3 minus 1, because n is 3, and this in the denominator we have the top is 3 minus 2, and the bottom is 3 minus 1. And so that is A to the first. If you do 3 minus 2, that's the first subscript, and A minus 3 is a subscript of 2. So we're doing A1 over A2. Well, we know what A1 is from right here. There's A1. There's A2, so that's going to be 1 over 2. So now we know our third term is 1/2. Okay, and so you see how in a recursive formula you have to use previous terms to get new terms. And so let's do that again. If I want the fourth term, according to this formula, that's going to be A sub 4 minus 2 over A sub 4 minus 1. That is A2 over A3. Do we know A2? Yes, that was given here, so we can plug that in. A2 we know is 2, so this number is A2, and A3 is the one that we just got done calculating, so A3 is going to go there, and that is 1/2. So our fourth term is 2 divided by 1/2, which is 4. Let's go ahead and calculate a couple more terms. A sub 5. If we see the pattern we're following, we're always subtracting 2 from the subscript for the top, so that's A3, and we're subtracting 1 from the subscript for the bottom, so that's going to be A sub 4. And so what we're doing each time to generate the next term is we're taking the quotient of the two previous terms. So A sub 3 we said is 1/2. A sub 4 is the one that we just calculated, that is 4. And so 1/2 divided by 4 is 1/8. Okay, so far our sequence goes like this. 1, 2, 1/2, 4, 1/8. Let's generate one more term. A sub 6 is going to be A sub 4 over A sub 5. So A sub 4 we calculated already, it was 4, and A sub 5 we calculated is 1/8, so that is 32. So now we know 32 is the next number in our sequence. And this sequence is going to continue going forever. Now notice the big difference with a recursive formula is I cannot jump to the 100th term or the 1000th term. I can't calculate the 100th term unless I know the two previous terms that came before it, because like we showed here, A sub 5 was the quotient of the two previous terms, A sub 3 and A sub 4. So if I wanted to know the 100th term, I can't get the 100th term unless I know the 98th term and the 97th term. So it would be A sub 98 over A sub 97. I don't know those, so I can't find the 100th term explicitly. I have to go through the whole recursive process, finding all of the terms that lead up to that. So that is a big difference that you'll notice with a recursive formula, is you can't jump ahead. You have to find the terms in sequence in order to get to the 100th term. I would have to generate all the terms from the first term all the way up to the 98th term in order to get the 100th term. Actually, let's see. I had the wrong subscripts in here. I would need 98 over 99 is what I would need. A sub 98 over A sub 99. In any case, we don't know those, and so we can't jump ahead. But if we continue, let's go ahead and find two more terms. So I'd like you to try these. See if you can calculate the 7th term and the 8th term. So go ahead and press pause on your video player, calculate the 7th term and the 8th term, and then see if you can make a determination on what the sequence is approaching, if any. Okay, so a sub 7 is a sub 5 over a sub 6, and we know a sub 5 is 1/8, a sub 6 is 32, and so we get 1 over 256. A sub 8 is this quotient of a sub 6 over a sub 7, and a sub 6 we got was 32, and a sub 7 we got 1 over 256, and that is 8,192. And so now if we look at what's going on with our sequence, we can see that it's going back and forth between really large numbers and really small numbers. So we had a whole number, and then a fraction, and then a bigger whole number, and then a smaller fraction, and then a bigger whole number, and then a smaller fraction, and a bigger whole number. And so this is just going to continue going back and forth like this to a number that's really small, getting closer and closer to 0, and then a number that's really large, approaching infinity. And so since this is not going to ever approach any particular number, they're just going to keep getting alternating between a larger a number that's growing toward infinity and a number that's approaching 0. We can't say that this sequence is approaching any particular number, so we'll say this sequence diverges. It does not approach any particular number. Okay, so now I would like you to press pause on your video and go ahead and try example D. This is another example of a recursive formula. And so see if you can generate 4 or 5 or 6 terms in this sequence, and then determine whether it converges or diverges. So go ahead and press pause, and don't press play again until you're all done and ready to compare with my solution. So example D is actually a famous sequence called the Fibonacci sequence. So the Fibonacci sequence starts with A1 equals 1, or actually in this one they started with a subscript of 0. So subscripts can start with anything really. Sometimes we see starting with a subscript of 0, sometimes with a subscript of 1. So this one we started with A sub 0 is equal to 1, A1 is equal to 1 also, and then A2 it says is the sum of the 2 previous terms. And so when we subtract 2 from the subscript, that's going to be A sub 0. And then when we subtract 1 from the subscript, that's going to be A sub 1. So we know A0 and A1. A0 is 1, and A1 is also 1, so we get 2. So now we know A2 is 2. And then that pattern continues. So A3 is going to be A1 plus A2. So basically it's just the sum of the 2 previous numbers. And so 1 plus 2 is 3. So our third number in the Fibonacci sequence is 3. A sub 4 is going to be the sum of the 2 previous numbers. 2 plus 3, that's 5. a sub 5 is the sum of the two previous numbers, 3 plus 5, that is 8, and so on. And so the Fibonacci sequence goes 1, 1, 2, 3, 5, 8, going on forever. So you can see right away that this is just going to grow without bound, so we can say this sequence diverges. It's approaching infinity. If we wanted to write that in a limit format, we could say the limit as n approaches infinity of a sub n is equal to infinity, which means it diverges. So now we've seen that sequences can be represented by explicit formulas and recursive formulas. So I've got three more examples here that I'd like you to try. So go ahead and these are all E, F, and G are all explicit formulas. So those are more similar to examples A and B. So I'd like you to go ahead and try each of these, E, F, and G. And so press pause on your video, try E, F, and G, and then when you're done with all three of those, come back and press play, and you'll see my solution. For example, E, if we take the limit as n approaches infinity of n squared plus 2n minus 3 over n cubed minus 4, we can see that the denominator has a larger exponent than the numerator, so that might be sufficient enough for you to realize that this expression is going to approach 0. We can prove that a couple of different ways. You could say the limit as n approaches infinity, if I divide everything by n cubed, I would have n squared over n cubed plus 2n over n cubed minus 3 over n cubed divided by n cubed over n cubed minus 4 over n cubed. And so then that is 1 over n, 2 over n squared, 3 over n cubed, 1 minus 4 over n cubed. So all of these fractions that still have an n in the denominator are going to approach 0. So those all approach 0. This approaches 0. So we just end up with 0 over 1, which is 0. So this limit is equal to 0. You could have also done that using L'Hopital's rule. Either way, you get that the limit as n approaches infinity of a sub n is equal to 0. Now 0 is a real number, so L equals 0. That tells us this sequence converges to 0. So that means the terms are getting smaller and smaller and smaller, getting closer to 0. If you list out a few of the terms, you will see that happening. In example F, we take the limit as n approaches infinity of natural log n over n squared. Both the numerator and denominator approach infinity, so we can apply L'Hopital's rule, and that will be the limit as n approaches infinity of 1 over n divided by 2n, which if we simplify that, we get 1 over 2n squared, and the denominator is growing to infinity, so that makes our fraction approach 0. So this one also has a limit equal to 0, and so that tells us that the sequence again converges to 0. Okay, and example G. If we evaluate this limit, we get 9/3. You can get that answer by using either technique, like we did in example E up here, dividing everything by, in this case we would divide everything by n squared, or you could apply L'Hopital's rule. Either way, you're going to get 9/3 or 3. So that tells us this sequence converges to 3, which means as we list the terms of the sequence, they will get closer and closer to 3. So you can plug in 1, you can plug in 2, you can plug in 100, you can plug in 1,000. You're going to see the larger n is, the closer these terms come to 3. Okay, so the next part of this lesson is to try to write our own formulas, explicit formulas or recursive formulas. So we're going to get a little bit of practice doing both. In the first example, we can see a pattern that we are, let's see, 2, 4, 6, 8. The next one would be 10 and so on. So these are just multiples of 2, and so we can say a sub n is just 2n. When n is 1, notice that when n is 1, we get 2 times 1, which is 2. When n is 2, we get 2 times 2, which is 4. When n is 3, we get 2 times 3, which is 6, and that fits our sequence exactly. So our explicit formula would be a sub n is equal to 2n. Go ahead and try example B. See if you can generate a formula, an explicit formula, that generates the numbers 1, 5, 9, 13, and so on. So press pause, and then start the video again when you're ready to see the solution. Okay, in this one we notice a pattern that the numbers are increasing by 4 each time. And so that has a what we call a linear relationship. Example A was also a linear relationship because we were adding 2 each time. So we're adding 4 each time, and we're starting with 1. So we can say that the nth term is going to be the first term plus we need to add a certain number of 4s, and so it's going to be, we added 0 4s to get the first term, and then 1 4 to get the second term, and another 4 to get the third term. So if we say it's n minus 1 times 4, that also can be written as 4n minus 3 if you multiply all that out and simplify. So our one way to write our term generating formula is a sub n is equal to 4n minus 3. And again, it's always a good idea to test it out and see if it works. A1 is equal to 4 times 1 minus 3. That turns out to be 1. A2, if you plug in 2, 4 times 2 minus 3, that's 8 minus 3, which is 5. A3 is going to be 12 minus 3, which is 9, and so on. So we see that this has the linear relationship that I was talking about. Our slope is 4, and you can also think of the negative 3 as being the y-intercept. If you wanted to come up with this formula by treating it as a line, this isn't, since we're calling this A1, A2, A3, you could think of these as the points 1, 1. So you put the subscript there and the value there. The second term, when n is 2, we get 5. And so since this is a linear relationship, you could find the equation of the line that goes through 1, 1 and 2, 5, and you'd get the same formula. Okay, so Example C is not a linear relationship. There's not a common difference from term to term, but we do see a definite pattern. The numbers in the top start at 2 and just keep increasing by 1. The numbers in the bottom start with 5 and just keep increasing by 1. And so we could say the nth term. So if we think of this as A1, okay, look at how the numbers on the top, this is A2, look at how the numbers on the top compare to the subscript. So when the subscript is 1, the numerator is 2. When the subscript is 2, the numerator is 3. When it's 3, we write 4. When it's 4, we write 5. So it's always 1 greater than the subscript. Okay, now look at the numbers in the bottom. When the subscript is 1, we write 5. When the subscript is 2, we write 6. When the subscript is 3, we write 7. So the denominator is always 4 larger than whatever the subscript is. That works for this one also. If I take my subscript of 4 and I add 4 to it, I get 8. So it looks like always our denominator is the subscript plus 4. So this is our term generating formula, a sub n. Again, you can test it out. If you plug in 1, you get 2 over 5. If you plug in 2, you get 2 for n, you get 3 over 6, which is 1/2. If you plug in 3, you get 4 on top and 7 in the bottom. So they seem to be matching the sequence that was given. Okay, so each one of these is kind of like a puzzle. There's not a set way on how to do any one of these. You're just trying to look for a pattern and then determine a way to write this as a formula. Okay, so go ahead and take a look at problems D and E. I'd like you to try D and E on your own. See if you can come up with a formula, an explicit formula, that will generate these numbers. So press pause and then start the video up again when you're ready to see the solution. So for each of these, we want to try to figure out if we write down the name of the term, we're calling that A1, we're calling this one A2, A3, A4, A5. We want to try to figure out what is the relationship between the subscript number and the fraction that we get. And so in this case, let's just focus on the tops. When A is 1, our numerator is 1. But then when A is 2, our numerator is 4. When A is 3, our numerator is 9. So what are we doing to the numerator, or what are we doing to the subscript to get the numerator? And so you might recognize what we're doing with each of these subscripts is we're squaring it. We square 4 to get 16. We square 5 to get 25. We square 1 to get 1, and we square 2 to get 4. And so in general, what we're doing is we're taking the subscript and we're just squaring it. And so it's going to be n squared in the numerator. Okay, so the numerator is one problem in itself, and now we go back and look at the denominators. What do I do with the number 1 to end up with 2? What do I do with 2 to end up with 5? So is there a pattern? Is there some relationship between our subscript and our denominator? I do notice that the denominators are going up by 3 each time. So from 2 to 5 is an increase of 3, from 5 to 8 is an increase of 3, from 8 to 11 is an increase of 3, and also from 11 to 14. So that is that linear relationship that we talked about earlier. And so we can see that since our change is 3 each time, we know it's going to be something to do with 3n. And then if I take 3n and I subtract 1, so in this case 3 times 1 minus 1 gives me 2. 3 times 2 is 6, minus 1 gives me 5, and so on. So our denominator is going to be 3n minus 1. Whenever you see a common difference like that, you can always use the formula, the first number plus n minus 1 times the common difference. So our common difference we said was 3. And so notice that when I expand this out, this is 3n minus 3, so that becomes 3n minus 1. That's the same thing we got by just analyzing the change. So this technique will always work. You take your first number, which was our first number 2, and then n minus 1 times the common difference. Our common difference from 2 to 5 and 5 to 8 and 8 to 11 was 3. So this is anytime you recognize that there's a linear relationship, you can always do the first term, that's the starting number, and then n minus 1 times the common difference. And you'll notice that going back to some of the previous problems that we did, like example B, that worked. First term, 1, n minus 1 times our common difference of 4. So anytime you recognize that there's a common difference from one number to the next, and that pattern continues, you can use that idea of first term plus n minus 1 times the common difference. So that may help you with those linear relationships. Okay, example E, again we want to compare our subscripts to the number that's being generated. Let's just focus on the top. So there's 1, 2 becomes root 2, 3 becomes root 3, 4, if we follow that pattern, that should be root 4, and that does work. 2 is the square root of 4, so it looks like in the numerator what we're doing each time is we're just taking the square root of n. Square root of 1, square root of 2, square root of 3, square root of 4. And then in the denominators, notice that these are all powers of 3. That's 3 to the first power, 9 is 3 to the second, 27 is 3 to the third power, and 81 is 3 to the fourth power. And so those powers match the subscripts exactly. And so we're just doing 3 to the n in the denominator. So there's our explicit formula for example E. The next thing we want to do is get some practice with recursive formulas. So remember, for a recursive formula, you need to provide the starting value and then what you're doing with each term to get to the next one. And so in this sequence, we're adding 7 to get from 7 to 13. From 13 to 20, we're adding 7 again, and then we're adding 7 again. So we see that common difference that we saw in some of the previous examples, but this time we want to write it recursively. So what we do is we say we're starting with a1 equals 6, and then to get every term after that, all we're doing is taking the previous term. So if you decrease the subscript by 1, that gives you the previous term, and then we're adding 7. Okay, so that's it. There's our recursive formula. We can test it out. If we start with a1 equals 6, according to this formula, a2 would be a1 plus 7. So that would be 6 plus 7, which is 13. That matches. Let's try another one. a3, according to our formula, that would be a sub 2 plus 7. And so that is a sub 2 we got was 13. 13 plus 7 is 20. And so this a sub n minus 1 is really giving us the previous term. So we're just taking the previous term and adding 7. So remember, for recursive formulas, you have to provide a starting point. Sometimes you have to provide 2 starting numbers. Okay? For example, B, here we have a different kind of pattern. We're multiplying by 2 each time. So multiply by 2, multiply by 2, multiply by 2. So we're just taking our previous term and multiplying it by 2 to get the new term. So our recursive formula is going to say we're going to start with a1 equals 5, and then to get any nth term, you just take the previous term and you multiply by 2. So it's going to be 2 times a sub n minus 1. So 2 times the previous term. 2 times previous term. Okay, and that should do it. So again, you can test it. A1 equals 5 as our starting point. A2 is equal to previous term times 2, or 2 times previous term. And so that would be 2 times 5, and that's 10. A3 is 2 times A2, and that's 2 times 10, or 20, and that works as well. Okay, so that one is correct. Go ahead and press pause on your player and try problems C and D. Press play when you're ready to see the answers. To write recursive formulas, we want to try to recognize what is being done to each term to get the next term. And so one thing you might notice is to get from 2/5 to 4/15, what we're doing is we're multiplying the top by 2 and we're multiplying the bottom by 3. And so what we're really doing is we're multiplying by 2/3. And then if you take 4/15 and you multiply the top by 2, you get 8. Multiply the bottom by 3, that gives you 8/45, which is our next term. So that is the common pattern, is we just keep multiplying by 2/3 to get the next term. So we can say our first term is 2/5. Our nth term is always the previous term times 2/3. So you're just going to write 2/3 a sub n minus 1. Okay, previous term times 2/3. Example D might be a little bit trickier than some of the previous examples. What you want to recognize again is what are we doing to each term to get the next term? So if I start with 3, I'm doubling it, that gives me 6, and then add 1 to get 7. Now I'm at 7, double it to get 14, add 1 to get 15. So we're multiplying by 2 and adding 1. Then we multiply 7 by 2, we add 1. If we multiply 15 by 2 and then add 1, that gives us 31. And do 2 times 31 plus 1 would give us 63. And so our recursive formula says start with 3, and then to get each term after that, double the previous term and add 1. All right, go ahead and give this one last try. Example E, see if you can recognize a pattern. What is happening from one term to get the next? What are you doing to 81/256 to get 9/16? What are you doing to 9/16 to get 3/4, and so on? So if you can recognize that pattern, go ahead and write the recursive formula. So for this one, you might recognize that all you're doing is taking the square root of 81 to get 9. So square root of 81 to get 9. The square root of 9 gives you 3. The square root of 3 gives you square root of 3. And then we can do the same thing in the denominator. The square root of 256 is 16. The square root of 16 is 4. The square root of 4 is 2, and so on. So all we're doing to get from one term to the next is we're taking the square root. So we start off with A1 equals 81/256. To get the nth term, all we're doing is we're taking the square root of the term that came before it. Okay, so that completes our notes for section 10.1. Now what I would strongly recommend you do is go to your textbook and go to page 572, try out all of these problems. Before you do any of the online homework assignment, try out these problems. The odd numbered problems have an answer in the back of your book. I will also post the written solutions to each of these problems on my website. So after you try all those, you can check the solutions in your book or check on my website for the the fully written solutions to each of these. So that completes our lesson. Thank you for tuning in, and then you can always go back and rewatch any of these parts if you need to again. Take care.